Hi, today we will discuss beams and frames, the internal loadings developed in these structural members. As an overview, I will give you the motivation, and then we will look at the internal loadings at a point, and then we will consider the sign convention, procedure for analysis, and some examples. Then after that, we will discuss shear and moment functions, including some examples. And lastly, I will show to you the relationship between load, shear, and moment. The big company leads the group at Grand Bay, Miami. As you can see, this is a twisted building with the corresponding columns or the external columns, which is quite clear on the picture. This is a conceptual building, but as you can see, uh, there is a core inside the building which actually holds the whole structure. The supporting columns or the outer columns actually uh, carries a different loading. I will tell you in the next slide. Accordingly, the column at the top, as you can see, since this is twisting, the column, according to this diagram, from the base of the column here up to the top of the column, it changes up to this portion. This is quite big twist. I think if I can estimate this 5 to 10 degrees twist of the building. So here, as you can see, actually the building or the outer column, this one is a hanging column. The structural engineer Vincent De Simon actually designed these columns to carry two kinds of forces. The yellow one is a tension force, and the red one has the compression. So this hanging column or twisted columns depicts two forces. Okay, but since the top portion of the column is in tension, this tension should be transferred to somewhere else. It should be transferred here. This is quite innovative solution, innovative structural solution, putting some rope girders, because the columns in tension should be carried by, or the tension force in this column should be transferred to these rope girders, and these rope girders or the force from the rope girders will be transferred to the core of the building. So as you can see, it's really challenging. It's really a challenge for a structural engineer for this type of building, but we can always look for an innovative solution for our problems. Also, you can see here, aside from the slanting column, the structural engineer was able to design a cantilever slab. This is quite impressive actually. Look at these slabs. These are flat slabs with no beams. Remember, this is in Florida, so the earthquake in Florida is not really that high magnitude, so they were able to use flat slabs in their buildings. So to design for that particular building, first we need to know the internal loadings involved at the the different members, and that is what we will be discussing today. First is that we would like to know the internal loadings for a specified point. So before a structural member can be designed, or in other words, proportion, it is necessary to determine the force and moment that act within it. Remember, force and moment. Remember that the internal load at the specified point in a member can be determined by using the method of section. That is, if we cut a certain portion of the member, we will be able to determine the internal load at that portion. So in general, this loading for ecoplanar structure will consist of first the normal force, that is 90 degrees with respect to the longitudinal axis, the shear force V, which is perpendicular to the longitudinal axis, and the bending moment M. Once these resultant internal loadings are known, the magnitude of the stress can be determined provided an assumed distribution of stress over the cross-sectional area is specified. Take note that these forces, the normal force N, the shear force V, and the bending moment M, are just actually resultants of the stress distribution over the cross-sectional area of the cut section. This is just to simplify our analysis. So look at the beam below. If we have to cut it at this portion, the left segment of the beam will be this one. The cut section will have the internal force or the normal force N, which is positive, assuming positive in that direction, a shear V going down, that is positive also, and the bending moment M, which is counterclockwise. But if you have to transfer this on the other segment of the beam, again you need to follow Newton's third law of motion, the action and reaction. They have the same magnitude but in the opposite direction, just like the normal force N. It's going to the right, but here it's going to the left, which is also positive. And the shear going down is positive. Here, shear is going up, which is also positive. Bending moment here is counterclockwise, which is positive, and on the other side, clockwise, on the positive for the clockwise. Again, these are just conventions. This is not an absolute value that it should be positive in that direction or negative. It depends on your assumption. But here we will just assume that the left segment, the normal force, is positive going to the right, and shear downward is positive, and bending counterclockwise is positive. So we will follow that one because it's very important that we will have a common sign convention. So before presenting a method for finding this internal normal force, shear force, and bending moment, we will need to establish this sign convention to define their positive and negative values. Again, although this choice is just arbitrary, the sign convention to be adopted here has been widely accepted in structural engineering practice, and it can be illustrated on the figure shown on the right. Looking at figure A, again, we just focus on a certain point, the portion that we cut. So we have the different forces N, V, and M in the positive direction. So for a tension to be, or for a force to be positive, it should be tension. That is, the arrow must act away from the base. So as you can see, left or right, as long as it is tension, or if the arrow is acting away from the face, then it is positive and it is tension. Also, for the shear force V, if the shear causes a clockwise rotation of the member, then it is positive. Remember, clockwise. So on the left hand side of this one, going up for this particular diagram, the third figure, and on the right side we have V, which is down. This will cause a clockwise rotation of the member, so this is positive. Look at the figure A. This is the left portion of the segment, and this is the right portion. So it seems like if we have to cut here, the shear here will be down, and if we have to cut here, the shear will be up, just like this one. Then if the moment causes the member to smile, just like this one, this is concave upward. If the bending moment will cause concave upward of the member, then the moment is positive. Of course, in accordance with Newton's third law, the unequal but opposite normal force, shear force, and bending moment must act on the right-hand face of the member at the section. Perhaps an easy way to remember this sign convention is to isolate a small segment of the member and note that positive normal force tends to elongate the segment, that's tension. Positive shear tends to rotate the segment clockwise. And lastly, positive bending moment tends to bend the segment concave upward or smiley. Or that is to hold water. It seems like it's a ball. We have used different concepts just to internalize our sign conventions. It's very important because as we go along, we should be able to know in what's direction, what is positive and what is negative. So for the procedure for analysis, we have the following procedure, which provides a means for applying the method of sections to determine the internal normal force, shear force, and bending moment at the specific location in a structural member. So for the support reactions, before the member is cut, remember, before we cut the member or section it, it may be necessary to determine the member's support reaction so that the equilibrium equations are used only to solve for the internal loadings when the member is sectioned. Also, if the member is part of a pin-connected structure, the pin reactions can be determined using the methods we have presented earlier. For the pre-body diagram, again, we always have to draw our pre-body diagram. It's very, very important. Keep all distributed loadings, couple moments, and forces acting on the member in their exact location. Then pass an imaginary section through the member, perpendicular to its axis at the point where the internal loading is to be determined. After the section is made, draw a pre-body diagram of the segment that has at least the least number of loads on it, and the section indicate the unknown resultants N, V, and M acting in their positive directions. In the use of the equations of equilibrium, moments should be summed at the section about axis that pass through the centroid of the member's cross-sectional area in order to eliminate the unknowns N and V and thereby obtain a direct solution for M. If the solution of the equilibrium equations yields a quantity having a negative magnitude, the assumed directional sense of the quantity is opposite to that shown in the pre-body diagram. So you don't have to hesitate assuming which direction that your forces or moment is going. As long as you have assumed it in a particular sign convention, and if the result is negative, then you just have to change the direction of your quantity. As an example, we have example 4.1 of HIBBELER 2005 up 15. Here is a building roof which has a weight of 1.8 kilopascal and is supported on 8-meter long simply supported beams that are spaced 1 meter apart. You can see the cross section here. Its beam transmits its loading to two girders. So there will be girder here in front and the girder at the back. Located at the front and back of the building. Determine the internal shear and moment in the front girder at point C here. And of course the problem says we have to neglect the weight of the members. So for a particular simply supported beam, the 8 meters simply supported beam, here is the details. We have the supports here and here at a distance 0.5 meter from the end of the girder and 0.5 on the other one. So the supports are 7 meters, but the whole beam is 8 meters. But the problem says this carries 1.8 kilopascal of loading. But since we only have, or these simply supported beams are spaced 1 meter apart, so the tributary area will be 0.5 on the left, 0.5 on the right, so that's 1. So 1.8 kilopascal times 1 meter, that's 1.8 kilonewton per meter. 1.8 times 8 meters, the whole length of the beam. So that's 4, 6, 14.2, no, 14.4 divided by 2, that's 7.2 kilonewton. So those are the reactions on the two supports. Sorry for that, I just calculated mentally the reactions, but you need to apply summation process, summation moment, just to compute for the reaction. But for this particular example, since it is just quite simple because of the symmetry of the structure and the loading, we can just multiply this loading with the total length and divide it by 2 to get the reactions. That's what I did. So as you can see, the front elevation here, we have applied the 7.2 kilonewton reaction here at a distance of 1 meter, except of course at the end, which has only 0.5 tributary width, so the reaction is also half of the reaction at the middle. So that's 3.6 and 3.6 on the other side. Again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 loads plus 1 half here, 1 half, so that's 12. 7.2 times 12 divided by 2, that's 43.2 kilonewton the reaction. Again, that is just a mental calculation of the reactions. But if you are not confident, you can always use the equilibrium equation. Summation forces is equal to 0 and summation moment is equal to 0 to determine the reactions here. After knowing the reactions, then we can just segregate this portion here. We have to cut this portion. Actually, you can choose the left segment of the cut or the right segment. Both are the same. But here we have chosen the left-hand side of the framing. So you can see here the pre-body diagram with the loadings and the shear and the moment. We haven't put the normal force because there is no horizontal force. So n for this particular problem is 0. So here, if we use the equations of equilibrium, we can just directly use summation forces vertical to compute for the shear at point C, that is V sub C. So if we have to sum up forces vertical, we have 43.2 kilonewton minus 3.6 minus 7.2 minus 7.2 minus V sub C, then equate to 0. In this particular problem, VC is equal to 25.2 kilonewton, which is positive. So meaning our assumption or the assumed direction is correct. Then solving for the moment, sum of moment at point C. So if a force will tend to create a counterclockwise moment, that is positive. A clockwise moment is negative. So here mz is counterclockwise, so that's positive. Mz plus 7.2 times 0.4 plus the other 7.2 times 1 and 0.4, that's 1.4, plus 3.6 times the distance 1.4, that's 2.4. Then minus the reaction, 43.2 kilonewton times the distance 1.2 meter, then equate to 0. Here the moment at point C is equal to 30.2 kilonewton meter. Again, the result is positive, which means our assumed direction of the moment, which is counterclockwise, is correct. Another example, we have to determine the internal shear and moment acting at a section passing through point C in the beam shown. Here we have a triangular force applied, triangular loading, so we need to compute the reactions again for this particular beam. So here the support reaction can be directly computed by using the equations of equilibrium, sum up moments here or here, and compute the different reactions. So that after that we can just cut the portion at the beam at point C. So here the segment AC on the left will be considered since it yields the simplest solution. Again, you can always look at the other side. It's not wrong that you have to use the right segment of the beam. But for simple solution, we just use the segment BC. But as you can see, the loading, the triangular loading should be proportion according to the actual beam. So here we have location of 6 feet from the left support, and this is 18 feet. So you just have to use ratio and proportion. In this case, the height is 1 kip per foot. I hope you know how to do some ratio and proportion or proportioning. We can now apply the equilibrium of equations. Summation forces vertical, that's 9 minus 3 minus VC equal to 0. Here, VC is equal to 6 kips, which is positive, so this is correct, going down. Summation moment at point C is equal to 0. 9, the reaction 9 will create a clockwise moment, so that's negative 9 times 6 plus 3 times 2, this will create positive moment, plus MC is equal to 0. So MC is 48 kilonewton kips foot. Also, of course, we have added the normal force NC, but in this particular case, since there is no horizontal force applied, so NC will be equal to 0. Another example, the 9 kip force below is supported by the floor panel DE. This one, this is a floor panel supported by which supports the 9 kips. As we have learned in the load path, this 9 kips will be transferred to the this panel. The panel will transfer it to this portion. This portion. So if this is concentrated load, the force will be transferred as a concentrated load at point D and E, and will be transferred above the girder at this portion. So we would like to determine the internal shear and moment acting at point C in the girder. So here is the basic representation of the diagram, the free-body diagram. 9 will be transferred to the simple supports, which is 6 kips, 3 kips, and will be transferred to the I-beam, and then I-beam to the girder, which is we have 6 at the corresponding distances. So in this particular case, we can compute for the reaction. You can sum up moment on the left or on the right to determine the vertical reaction. So of course, you can consider the load above, or you can consider the loads as applied at the girder. In which way you will go, the results will be the same. So if we have to cut the segment, this is the free-body diagram of the segment with the left support 3.75 kips and the loading 6 kips, and here again we assume NC tension as positive, VC going down as positive, MC clockwise or counterclockwise as positive. So we can now directly use the equations of equilibrium, where VC is minus 2.25 K, meaning our assumed direction is incorrect. So we will just redraw or say that VC is going up. Sum of moment at point C, MC is equal to 38.25 kip foot. Again, since it is positive, our assumed direction is correct. So much for that, because it's very important to at least recognize or have some ideas on the concept of the internal shear and moments, or the internal forces and moment at a particular point. But we are not actually interested on one point only. Most often, we would like to know the internal loadings along the whole beam or column. So in this way, it would be easier if we can have a general function, a function for shear and a function for moment. Another way of saying functions is equations. We should have an equation in terms of shear and in terms of moment, so that we can easily determine the shear and moment for the whole section of the beam. It's not just for a particular point. So the design of a beam requires a detailed knowledge of the variations of this internal shear force and moment acting at each point along the axis of the beam. And that would be really difficult if you have to do it one by one. So it's very important if we can find a function for that. The internal normal force is generally not considered, of course, for two reasons. If you notice, we only consider shear and bending moment. And here are the reasons why we did not include the normal force. First case is that, or first reason is that most cases, the loads applied to the beam act perpendicular to the beam's axis and hence produce only an internal shear force and bending moment, no axial force. The second reason is that for design purposes, the beam's resistance to shear and particularly to bending is more important than its ability to resist normal force. Of course, an important exception to this reason number two, of course, that is when beams are subjected to compressive axial forces, since the buckling or instability that may occur has to be investigated. So you have to make sure if there will be no compressive axial force applied to the beam. Otherwise, you can just neglect the axial force or the internal normal force. The variations of the shear and moment as a function of the position x of an arbitrary point along the beam's axis can be obtained by using the method of sections. However, it is necessary to locate the imaginary section or cut an arbitrary distance x from one end of the beam rather than at a specific point. In general, the internal shear and moment functions will be discontinuous. Remember, these functions will be discontinuous. This is quite different to the functions that we used to solve. Or their slope will be discontinuous at points where the type or magnitude of the distributed load changes or where concentrated forces or coupled moments are applied. So this is the crucial part of the shear and moment functions. Remember, it is continuous or the slope will be discontinuous. So we have to check that one. But anyway, it's quite easy to apply that one. The shear and moment functions must be determined for its region of the beam located within two discontinuities of the loading. So remember, if you find some discontinuities of loading, then you have to define your function within that region only. Okay. So as we mentioned, shear and moment functions must be determined for its region of the beam located between any two discontinuities of loading. For example, for coordinates x1, x2, x3 will have to be used to describe the variation of v and m throughout the length of the beam below. These coordinates will be valid only within regions from A to B for x1 because there is a discontinuity at point B, that is the load W ends at point B, and from point B to C for x2 and from C to D for x3. So note that it may be easier to develop the shear and moment functions using coordinates x1, x2, x3 for having origins at different points, that is at A, B, and D as shown in the right figure. Here x1 and x2 are positive to the right and x3 is positive to the left. Here is the procedure for analysis. The following procedures provides a method for determining the variation of shear and moment in a beam as a function of position x. For the support reactions, again, determine the support reactions on the beam and resolve all the external forces into components acting perpendicular and parallel to the beam's axis. Remember, for all the forces applied or reactions, it should be resolved into its components, that is perpendicular or parallel to the beam's axis, so that it would be easier to apply it in the shear and moment equations. For the shear and moment functions, you have to specify separate coordinates x and associated origins extending into regions of the beam between concentrated forces and or couple moments, or where there is a discontinuity of distributed loading. Section the beam perpendicular to its axis at its distance x, and from the free-body diagram of one of the segments, determine the unknowns v and m at the cut section as functions of x. On the free-body diagram, v and m should be shown acting in their positive directions. In accordance with the sign convention that we have mentioned earlier, v is obtained from the summation forces is equal to 0, and m is obtained by summing moments about the point S located at the cut section. The results can be checked by noting that the slope, that is the change in the moment with respect to x, is equal to the shear, and the change in shear with respect to dx is equal to the loading W, where W is positive when it acts upward away from the beam. These relationships can be are developed in the next sections. We mentioned about the load discontinuity, so you need to be careful with this one because its function should be within the region of the load discontinuities. These load discontinuities are shown when there are point loads, applied moments, structural supports, beam ends, and abrupt changes in load intensity. So by just remembering these 5 points, you will always be able to determine the load discontinuity of the beam or frame. So here is the example 4.4 of HIBBELER 2015 to determine the shear and moment functions of this particular beam. We would like to determine the shear and moment in the beam shown as a function of x. So here we need to determine first the reactions. So you can just use the equilibrium equations, summation forces and summation moment, to get this corresponding reactions 30 keeps up and bending moment 600 keep put counter clockwise. For the shear and moment functions, it's easy if we can just cut the portion of the beam, like for example the certain portion here for a particular x distance. So you need to determine the height of the loading here uh, at x distance. So you can just use a ratio and proportion. This height is to this total height 2 kips per foot of is equal to the distance x is to 30. So that's around 2 times x over 30, that's 1 over 15 x. So here W is 1 over 15 kip per foot, and the distance is x. So the resultant of this triangle is 1/2 of this distance x times the height x over 15. So that's 1/2 x over 15 times x. So if we have to sum up forces vertical, that is 30 minus 1/2 of x over 15 times x minus v is equal to 0. So here is the equation solving for b, which is a function of x. So v is 30 minus 0.033 x squared. So this is the function that we are looking for this beam. So this is the function v is equal to 30 minus 0.033 x squared. So you can find actually the shear at any point of the beam by just using the value of x. Also, if we sum up moment at s is equal to 0, we have the moment 600, that's positive, minus the shear or reaction 30 times x, plus 1/2 x over 15 times x times the centroid of this resultant, that is x over 3, plus the bending moment m. So equate that to 0 and solve for m. M is minus 600 plus 30x minus 0.0111 x cubed. So again, we can use this function for the moment m for any value of x. Of course, if x is equal to 0, that is at the reaction, your shear is 30. That is shown as the reaction. And here, when x is 0, your moment is minus 600, or this one. It should be 600. So as you can see, the shear from the triangular loading that is with a slope of 1, your shear will have a second degree slope x squared. So this is 2, and the moment is x cubed. So actually, from the loading to shear to moment, the slope increases by 1. So 1 for a triangle, 2 for the shear, that this is parabolic, and 3 for the moment, which is cubic. Take note that the change in the moment with respect to x, that is, take the derivative of dm with respect to x, that is equal to 30 minus 0.0111 times 3, that's 0.0333 x squared. That is equivalent to this shear v. So the change of the moment with respect to x is equal to the shear v. Or take the derivative of v with respect to x, that's equal to minus 0.0333 times 2, that's 0.0666 x, or that is equivalent to minus x over 15, or this is actually equal to the loading w. Uh, this of course will be used to serve as a check of the result. Anyway, we will talk more about this relationship in the coming discussions. So here, using the equations that we have derived, you can plot that one using your spreadsheet software. It's quite easy. I just use different distances from L is equal to 0 up to the length L, that is 30 feet. So here, from 0 to 30 feet, I have drawn the loading. This is the loading, the first column. So this is a straight line uh, with a slope of 1. The shear V at any distance from 0 to 30, I got these values, and I tried to plot that one, and it gave me a parabola which has a degree of 1. So as you can see, it decreases towards the length L. And so with the bending moment, and then I draw the moment diagram from negative 600 to 0 using these equations. Okay, so this is quite simple. If we did what we did earlier to look for the shear and moment at every point, then it will take time for us. But since we were able to determine the function, we can just use the spreadsheet software, or any software actually that can draw or make some visualizations. Okay, or you can use the GRAS. You can check it using the graphical rapid analysis software of structures of program, or the software. As you can see, I model it to be a cantilever beam with the loading of triangular loading 2.0. This is the loading diagram. As I analyze it, it will give me the shear force diagram here, actually the same with the one that we have done, and the bending moment is here. See, the results are the same. Of course, the software also computes for automatically computes for the support reactions and for the elastic curve to be drawn, or the elastic deflection curve. So with the corresponding displacements. Anyway, we will talk more about this portion, the elastic curve, in the coming discussions. Another example is to determine the shear and moment in this particular beam as a function of x. Again, in this particular problem, uh, it, really, it really depends on you, on where you will be starting, or as looking for the origin. For this particular segment, for keep or put, this is of distance 12 feet, you can assume your x starts from the left, or you can start from the right. In this case, if we assume x1 starts from the left, and then also x2 starts from the left, but to the second segment, after the discontinuity here, we have this another region. So we actually have two regions here. Or you can just assume x3 to start uh, after the discontinuity here at the uniformly distributed load, or it should start at the pre-end of the beam. It depends on you. You can always do some flexibility, but at the end of the day, the result should be the same. So here we have to compute first for the reactions. Again, you have to use equilibrium equations to compute for the reactions. So I will leave it for you to check the results. Then we can have the shear and moment functions. So first, we have for the first region, this one, under the 4K per foot loading, and we have this particular uh, portion. If we have to cut at this portion, it will give us this free body diagram that is at a distance x1. So we can easily compute for the shear here and the moment. Also, if we have to cut at the second region here, assuming that x2 is also coming from the left hand portion of the beam, then it will give us this diagram also. So using those diagrams, we can now apply summation forces. For the first segment or the first region, you can apply summation forces y is equal to 0. So that's 108 minus 4x1 minus v is equal to 0. The shear function is 100 minus 4x1. Here, in particular, the loading is the slope is 0, so we have to add 1 degree for the shear, so that's why this is x1. So this is a linear equation. If we sum of moment, we will be able to compute for the moment m minus 1588 plus 108 x1 minus 2 x1 square. Again, the degree will increase by 1, so that is why this is parabolic. For the second segment at 12 feet to 20 feet, we can apply again the summation forces y to compute for v. As you can see, the shear here is constant, which is equal to 60 because there is no loading in this region. The summation of moment is also equal to 60 x2 minus 1300. Again, notice that the degree is just one step higher. So from no loading to the shear with 0 degree and to the moment with 1 degree. I hope you will remember this one because as you draw the shear and moment diagram later on, we will do some shortcuts to draw it, and you can always remember these characteristics that I have mentioned to draw your shear and moment diagram. Again, note that the change in the moment is simply equal to the shear, and the change of shear with respect to x is simply equal to the loading w. Using the graphical rapid analysis of structures program, I have modeled it again here, and you will see the results here, the shear and the moment diagram. And of course, if you just have to draw this using these equations using software like the spreadsheet and other visualization programs, the result will be the same. But I will not give it or show it to you. I will ask you to do it so that you will also be able to see the results, and you will be developing your skill in structural engineering. And lastly, I want to show to you the relation between the load, shear, and the moment. If we have to consider an element of the beam of length dx, this particular element is loaded with a uniform load of magnitude w. So here is the isolated portion of the cut beam, but take note this uniform load w does not have to be uniform. It is also possible if it is not uniform, but for this particular analysis we assume that this is to be uniform. So to determine the shear and moment at the left end of this element, that is at section 1-1, we can just directly compute the moment or the shear here and the moment. So we have the shear here v and the moment m, and on the other side of this element is that the shear increased by dv and the moment is increased by dm. So the shear at section 1-1 is simply equal to v minus this portion, or simply V11 or the shear at B11 is simply equal to the left hand side REY minus the load P minus W times the distance A. And to compute for the moment, we have REY times the distance X minus the loading P times the distance B plus A minus this uniformly distributed load W times the distance A times 1/2 of A. So these are the shear and moment functions on the left of section 1.1. But if we move a distance dx from section 1.1 to section 1.2 at the right end of the element, then there will be new values of shear and moment. And this can be written this way. We just have added actually minus w dx to our previous equation. And for the moment, we have added v11 dx minus w dx squared over 2. Note the changes in these values may be expressed as the change in shear and the change of M respectively. This one, the change of shear is equal to minus W dx, and the change of M is B11 dx minus W dx squared over 2. So that from these expressions and with reference to the figure below, the changes in shear and moment in a distance dx are dv over dx, take the moment or the shear or the first derivative of the shear v with respect to x. Here it is equal to minus w. And also if we have to take the moment of m with respect to dx, the result will be only this portion, the shear v. How about this one? Actually, this should be added, but this is very small, infinitesimally small, because dx is very small, and a very small number square it, then it becomes smaller. So that's why the change in moment with respect to x is only for the shear v. And from that preceding expression, the change in shear from one section to another can be written as change in shear is equal to the integral of negative w dx from section 1.1 to section 2.2. And the change in moment in the same distance is delta m is equal to the integral of v dx from from 1-1 to 2-2. Note that a particular value of dv dx or dm dx is good only for the portion of the structure at which the function is continuous. Here, the two relationships are very useful for the structural engineer. We have the first equation that we have derived. The equation actually indicates the rate of change of shear at any point, which is equal to the load per unit length at the point, meaning the slope of the shear diagram at any point is equal to the load at that point. Remember, the slope of the shear diagram at any point is equal to the load at that point. The second equation indicates that the rate of change of moment at any point equals the shear, or this relation means that the slope of the bending moment curve at any point equals the shear. So looking in terms of integrals, the following relationships exist. The load is equal to W, the shear is equal to V, which is negative integral of W dx, and the moment M is equal to the integral of V dx, or the negative double integral of W dx. Or in terms of derivatives, the relationship will be the load is equal to W, which is dV minus dV over dx, or minus d square m over dx square, and the shear is equal to V, which is equal to dm over dx. These relationships in terms of integral and derivatives are very useful in the study of the shear and moment diagrams of beams and frames. So I hope you really need to understand this one and be able to apply this in drawing our shear and moment diagrams of beams and frames. That's all for this topic, and I hope we can give you some examples in the next videos. Thank you for